everyone, and welcome to this video about waste to energy, or WTE for short. Today, we're going to explore how converting waste into energy can help transition our communities to cleaner, more sustainable power sources. By the end of this training, you'll understand the role of waste to energy in the clean energy transition, key policies and regulations that support waste to energy, different waste to energy technologies, along with their benefits and challenges, environmental impacts of waste to energy, and methods to handle and utilize organic municipal waste, and how to remediate landfills for methane capture. Let's get started. Why waste to energy matters. Waste to energy plays an essential part in our shift away from fossil fuels. Every day, our cities and towns produce large quantities of non-recyclable waste. Instead of sending it all to landfills, waste to energy technologies can convert residual waste into electricity, heat, or other usable forms of energy. By doing so, we lower greenhouse gas emissions, as diverting organic waste from landfills cuts down on methane emissions, a potent greenhouse gas. Secondly, we reduce fossil fuel use, because energy produced from waste helps offset the need for coal, oil, and natural gas. Additionally, we support waste management goals, as alongside recycling and composting, waste to energy helps manage the portion of waste that cannot be easily recycled. And finally, we foster a circular economy. Recovering energy from waste materials ensures fewer valuable resources go unused. While waste to energy isn't a magic bullet, it can act as a bridge technology until we fully develop and scale up more renewable sources like solar, wind, and geothermal energy. Key policies and regulations. In Europe, waste to energy is supported by a robust policy framework that emphasizes waste reduction, sustainability, and lower emissions. Here are some of the most relevant policies. The first one is the European Waste Framework Directive. It lays out principles for reducing, reusing, recycling, and responsibly disposing of waste, and encourages waste to energy projects to handle residual or non-recyclable waste. The second relevant policy is the EU Landfill Directive, which seeks to reduce the environmental impacts of landfill disposal, and promotes waste to energy as a strategy to divert waste from landfills, mitigating methane release. Then we have a Circular Economy Action Plan, which focuses on reducing waste, maximizing resource use, and enhancing recycling, and recognizes waste to energy as a complementary tool for non-recyclable materials. Fourthly, there is a Renewable Energy Directive, which sets ambitious targets for renewable energy. It includes certain waste to energy technologies in the renewable energy mix, helping achieve climate goals. The fifth relevant policy in this context is the EU Green Deal, which is a broad agenda for climate action and carbon neutrality. It supports waste to energy to reduce landfill reliance and recover resources. And finally, the EU Emission Trading System, which is a cap-and-trade framework to reduce overall carbon emissions. It encourages lower emission alternatives and recognizes the potential for waste to energy to reduce methane from landfills. Overview of waste to energy technologies. Waste to energy isn't a single technology. It's a category describing multiple processes. Each has its own advantages and challenges. Let's review a few major ones. The first technology is incineration. This process includes burning waste at high temperatures to generate heat and electricity. The benefits are significantly reduced waste volume and captured energy to supply power to local grids. One of the challenges is that this process requires strict emissions control to manage pollutants, and additionally, leftover ash must be handled carefully. Then we have gasification. In this process, waste is converted into a synthetic gas, or syngas, by using high temperatures and limited oxygen. As a benefit, it produces a versatile gas that can be turned into electricity or other fuels. In this process, the challenges include complex technology and higher initial investments. The third technology is pyrolysis, where organic waste is heated in the absence of oxygen, producing bio-oil, biochar, and syngas. As a benefit, it converts diverse organic materials into multiple valuable byproducts. However, it can be challenging because pre-treatment of waste is often necessary, and it can be energy intensive. The fourth waste to energy technology is anaerobic digestion, which breaks down organic waste such as food scraps, agricultural residues, and more, without oxygen, creating biogas. The benefit is that biogas can be used for heat and electricity, and the leftover digestate can be used as fertilizer. However, this process only works effectively with organic materials, and managing the digestate properly is crucial. The fifth technology is landfill gas recovery, where methane is captured from decomposing waste in landfills. As a benefit, it prevents methane from escaping into the atmosphere and repurposes it as an energy source. However, it is dependent on landfill conditions, and leaks can undermine environmental benefits. The next technology is plasma arc gasification. In this process, extremely high energy plasma is used to break waste down into syngas. It is potentially very efficient and can handle hazardous waste. It is challenging because of high operational costs and is complex to run at a large scale. The seventh technology on our list is refuse-derived fuel, which converts non-recyclable waste into fuel pellets. As a result, the main benefit is a concentrated and relatively uniform fuel that can be combusted for energy. As a challenge, it requires sorting and can still produce emissions during combustion. And finally, hydrothermal carbonization, which uses high pressure and temperature to transform wet waste into hydrochar. The main benefit is that it's good for high moisture waste, like food scraps. However, it is still an emerging technology that requires further development. Benefits and challenges. Each technology offers unique benefits such as energy production, whether through biogas, syngas, or direct combustion. Waste-to-energy generates electricity or heat to power homes and businesses. An additional benefit is reduced landfill use. Converting waste to energy helps free up landfill space and lowers greenhouse gas emissions. And finally, circular economy alignment. Waste-to-energy complements recycling and composting by handling waste that can't be easily recycled or reused. However, there are notable challenges. For example, emissions control. Combustion-based processes can release pollutants. Proper filtering and regulation are essential. The next challenge is high capital costs. Technologies like gasification or plasma arc gasification can be expensive to set up and maintain. An additional challenge is public perception. Some communities worry about air quality and health impacts from waste-to-energy plants. Transparency and rigorous environmental monitoring are key. And finally, feedstock variability. Municipal waste composition can vary, affecting the efficiency of waste-to-energy systems. Consistent sorting and pre-processing are often needed. Environmental impacts of waste-to-energy. Waste-to-energy can offer an advantage over landfilling by reducing methane emissions, but it's not without trade-offs. Firstly, greenhouse gas emissions. Converting waste into energy reduces reliance on fossil fuels. However, the combustion processes do produce CO2. The net greenhouse gas impact often remains lower than sending waste to landfills, particularly if methane capture in landfills is suboptimal. Secondly, air pollutants. Incineration and pyrolysis can emit particulates and chemicals like nitrogen oxides or sulfur dioxides. Strict emission regulations, improved filters, and advanced technologies can mitigate these impacts. Thirdly, life cycle assessments. Studies show that waste-to-energy systems can help reduce overall carbon footprints, but may contribute to acidification or eutrophication if not carefully managed. The actual environmental benefits hinge on technology choices, waste composition, and pollution control measures. And finally, anaerobic digestion, which is typically seen as more environmentally friendly than incineration because it captures biogas and the digestate can enhance soil fertility. However, it still requires attention to odor control and proper handling of the residual materials. Managing organic waste. One key component of waste-to-energy is handling the large volume of organic waste produced by homes, restaurants, and public areas. Rather than letting it rot in landfills, here are some strategies. For example, composting, which is ideal for yard trimmings, food scraps, and other biodegradable materials, and produces nutrient-rich compost that enriches soil and supports agriculture. The second strategy to manage organic waste is anaerobic digestion. It transforms organic waste into biogas for energy and digestate for fertilizer. It is particularly relevant to municipalities aiming to reduce landfill use and carbon emissions. The third option is valorization. Using organic waste as raw material in other processes, like animal feed or specialty bio-based products, helps build a circular economy. Additionally, there are machine learning applications. Emerging tools, like artificial neural networks, can optimize processes, sorting waste, predicting yields, and improving treatment efficiency. And finally, bioreactor landfills, which are a more advanced type of landfill that circulates leachate to speed up waste degradation and can enhance the capture of methane for energy use. Landfill remediation and methane capture. Even with robust waste-to-energy initiatives, landfills will remain a part of our waste management landscape for the foreseeable future. Properly managed and remediated landfills can play a significant role in clean energy transition. Firstly, it's important to address cover systems. Placing barriers on top of landfills reduces water infiltration and gas emissions, improving air quality and minimizing leachate. Secondly, leachate collection and treatment requires some attention, as it stops pollutants from contaminating groundwater. Properly treated leachate protects human health and surrounding ecosystems. The next important point of landfill management is gas collection and utilization. Pipes and wells capture landfill gases, mostly methane, for flaring or generating electricity, which reduces potent greenhouse gases and provides a local energy source. Additionally, it is important to consider bioremediation. It uses microorganisms to break down or neutralize contaminants in the landfill. It can be more cost-effective and environmentally friendly than purely chemical options. The next point is excavation and off-site disposal. For severely contaminated sites, removing waste entirely may be necessary, though this approach is costly and disruptive. And finally, chemical oxidation or reduction, which assumes injecting chemicals into the landfill to treat contaminants in place. It is effective for targeted issues, but requires careful monitoring and can be expensive. Methane capture for electricity generation. Methane is a greenhouse gas, many times more potent than CO2 in its ability to trap heat in the atmosphere. Capturing methane from landfills or anaerobic digestion systems allows us to generate renewable electricity, as methane can be burned in turbines or engines to produce power. It also helps reduce greenhouse gas emissions, as preventing methane from escaping into the air is a major step in combating climate change. Additionally, it can benefit local economies, because landfill gas-to-energy projects can create jobs in system installation and maintenance, and produce revenue if the energy is sold to the grid. And finally, it improves public health. Properly managed landfills with gas capture reduce odors and fire risks, contributing to healthier living conditions for nearby communities. Conclusions and key takeaways. Waste-to-energy is not a one-size-fits-all solution, but it's a vital component in a broader clean energy and sustainability strategy. By combining waste-to-energy with robust recycling and composting programs, and by enforcing stringent environmental controls, municipalities can reduce reliance on fossil fuels, lower methane emissions from landfills, generate valuable electricity or heat, advance circular economy principles, and support local employment and economic growth. Above all, success in waste-to-energy depends on choosing the right technology for the local context, ensuring strict pollution control, and aligning projects with long-term climate and energy goals. Thank you for watching. And remember that the final goal is always to reduce the total amount of waste while maximizing resource recovery and minimizing environmental impact. If you're curious about more details or want to get involved in local clean energy initiatives, feel free to contact municipal authorities or environmental organizations in your region.